This is 9, 28, 16. This is what you did in the lab, is graph position against time. Now, the goal was that you had one thing that moved at a constant speed, a constant velocity, and you had one thing that moved at a changing velocity. That was the goal. I know it was a little funky. You know this, because you've already been doing problems with this, that the average velocity is how far it travels and how long it takes it to travel. If something is moving at an absolutely constant velocity, what would you expect that line to look like when you have position over time? Time is always the x. Straight line, curved line, straight line. Yeah, you guys know this. So constant velocity is going to show up on a position time graph as a straight line because the rate of change in position isn't changing. How many of you are in calculus? Okay, about half, which is a good mix. That's a good mix. I will toss this out. If you're not in calculus, don't worry about it. Have you done first derivatives yet? Okay, well then never mind. Nobody gets it. Moving on. So, if this is change in position over time, what would the slope of this line give you? Position over time. Change in position over time. Oh gee, we call that delta x. Oh gee, we call that delta t. Guess what the slope of this line shows you? Velocity. Does that immediately help on something with your lab? It may or may not. We're going to... So with this intuitively, and this is basically a physical science concept, the next thing that you probably got intuitively is, if I give you these three lines, which one of those objects is moving the fastest? A, B, or C? A. Steep line, high slope, faster average velocity. Low slope, lower average velocity. Good? Okay. Now, let's do one more thing. I'm going to shrink this. Set it aside. And I'm going to get rid of a couple of these lines. Because here's my next question for you. Is that object speeding up or slowing down? It's constant. Oh yeah, never mind. We're not doing changing yet. Jeez. Okay. Thank you. Do we know what direction this is moving in? The object.
Forward, as if the distance is increasing.
Okay. So about half of you said, no, we can't tell that from the graph. A few people kind of twitched, and you say forward.
As if the distance is increasing.
Okay. Forward or up is good. Basically, it's moving in a positive direction. So with motion, what we start to do, if you imagine a railroad car tied to a track, and it can only move one way or the other. Now if we make that track a number line, what we start to see is motion in a positive direction, motion in a negative direction. Mind you, positive and negative are arbitrary. We typically assign them, we have this thing imposed on us really early called the Cartesian coordinate system. Descartes was a creep, but he did give us, oh, seriously, ugh, creepy human being. But he gave us this. So we tend to, by default, use the Cartesian coordinate system and say that this is positive, this is negative. You can see where this will go when we start to talk about the y-axis. Up tends to be positive, down tends to be negative. So when we look then at this line, we can't say if this is moving north, south, east, west, left, or, 32 degrees west of north. but we can say that this is moving in the direction that we have called positive. Okay? So, constant velocity moving in a positive direction. What about this object? Moving in a positive or negative direction? Negative direction. Again, we can't say if that's left, right, north, south, up, down. It's whatever we've decided to call a negative direction. So if we have this object and it heads, goes that way, the graph for that motion is going to look like this. If that object does this, what's the graph going to look like? Great sign language, guys. So we're going to have something like that, right? So you're going to see representations of the positive and negative direction of travel in a graph of position time. Good. Okay, there's a big difference between the instantaneous velocity and the average velocity. If you go out, get in your car, start it up, and drive from here to Boardman, you can figure out an average velocity for that trip. And my best guess, based on personal experience, let's see, Rogers is 10 kilometers, and I'm going to say it's about 25 kilometers to Boardman, and it's probably going to take you 45 minutes. So 25 kilometers divided by 45 minutes, whatever that works out to in meters per second. Are you going that speed when your engine starts? Let's hope not. Are you going that speed through the snake bends on Route 7? Once again, let's hope not. You're all nice people. I'd like you to all make it intact through your trip to Boardman. So our average velocity for anything is very, very different than our instantaneous velocity. When you have an object that's moving at a changing speed, which you should have had with your marbles, how did the two tracks joined up work? Did that work? Did you try that, or did you use? You didn't try it. Okay. Did anybody try it?
We thought it was already going because it was already like really
8 feet long. No, I was hoping you would go for a 16-foot long marble track. I'll tell you why. Did you find that it was hard to get an additional data point with only 8 feet of marble track? It usually is. You don't really have enough data points to make an awesome line, and I was hoping. This year I had the great brainstorm, like, ooh, I should have them put all the marble tracks together. That would be fabulous. So then I wasn't here to suggest it, so I just wrote it down. But that's okay. But your marbles did move with changing velocity, correct? The rules of gravity were not suspended in this room while I was gone, I assume. I always want to check on those things. So you know that the graph of that motion is going to look different. You're not getting a straight line anymore, because now, for every amount of time, the amount of change in position is doing what? For the marble, anyway. Is it increasing or decreasing? Those are your options. It's increasing, because what is happening to the marbles? We'll talk about its speed right now. We'll leave off the velocity because we're just going to assume direction. So every second that it travels, its speed is doing what? Increasing. It's speeding up. So the graph of motion that is doing that is going to look something like that. What's the rate of speed in this section? Relatively low. Well, then that line, the slope changes, the slope gets higher, meaning the velocity is increasing. You know, obviously there's some point at which the marble melts and we've reached terminal velocity. You're not likely to do that in 8 feet of drywall corner marble track. That's a picture of an object that's speeding up. Traveling in what direction? Positive direction. Good. Now, riddle me this. Whoops. That didn't work out as anticipated. What's that object doing? Disagreement in the ranks. I like it. Good. Okay. Talk to somebody near you. See what they think. See if you think that they're full of it. Okay, but a little improvement to the drawing through enlargement of the screen. What happened here? Okay, I should rephrase that. We don't know what happened, but in general terms, this object started off at a tremendous rate of speed. Came off the start like bats. I don't know. Then it slows down. The rate of speed decreases, and here we have a slope of that line that is, slope of a flat line is? Slope of a flat line is? 0. And remember, we said that the slope of the line is equal to velocity. When that line goes flat, your velocity is 0. The steeper that slope, the faster that object is moving. So this is, let's look at one more object in motion here. And this might be a more realistic depiction of something. Okay. With apologies for bad drawing. Describe, so look over that line. Let me fix that up a little bit. Okay. Look over that line. Create a narrative for yourself. What is happening to this object? And remember, we're just describing its velocity. And then tell that to the person sitting next to you. See if you agree on a narrative. What do we know about this object?
Sped up, then hit a max.
Okay. So starting off, and if I fix this line here, started off, slow, sped up pretty quickly. Rate of change, it really speeds up here, and then what happens? Slows down, comes to a stop. If this object was returning back to whatever our arbitrary 0 point was, what would this line look like? So here it's all moving in a positive direction. It's all moving away from our 0 point in a positive direction. If it returns to base, whatever our arbitrary 0 mark is, whatever start is, we see this. Okay? I think for the most part this is pretty intuitive, but I think maybe it's actually good to have this discussion after you've done some graphing of objects moving in real time. Should all of your best fit lines be straight? No. You're going to have, now you also have 2 different kinds of graphs. You have 4 graphs total for this. So you have change in position, which is this. It's how far away from 0 you are at each little interval. There's another thing, however, that you talk about in this lab. In each time interval, so 2 to 3 seconds, 3 to 4 seconds, etc., the amount of change in position. So let me ask you this. If I am moving at a constant velocity, so my rate of speed is not going to change. I'm locked in at a rate of speed. I've set the cruise control, and it's perfect cruise control. For every single unit of time, should the distance that I travel change? No. So, in that 2 to 3 second interval, if I travel that far, how far should I travel in the 3 to 4 second interval? That far. And how far should I travel in the 4 to 5 second interval? That far. That's a different line. Now, does the slope of this line give you velocity? It doesn't. It gives you something different. And this isn't a graph that we talk about or use as much. Okay, go take your 4 minutes. We'll come back. So we're back to here. What would the best fit line be? Let's actually practice a best fit line for some slightly more realistic data. Hey, I got this kind of data for my car. It was supposed to be moving at a constant velocity. This is the distance that it moved in each time interval. What should my best fit line look like here? Okay, so there are, that's a good answer. There are two things going on here. Let's assume that the car was actually behaving perfectly. That the car was not doing all the weird stuff it does because the batteries wiggle or whatever. What should the distance that it traveled in each time interval have changed? No. If the cruise control is on and it's perfect, it should move the same distance in every single time interval. So if that's true, the aberrations that we're seeing in data are more related to the quality of data collection, which is totally normal. You're using, let's say sketchy at best instrumentation. We don't have, space age anything. We'll get some space age stuff. What would you expect the trend line to be here? Straight line. And actually, if you look at this data, this is not actually terrible data. Because if you do that, do you have some points above and below the line? Yeah. Are you shooting the average on that line? Yeah, you are. Some of you look profoundly unhappy with this. It chafes a little bit, doesn't it? Because darn it, you want to connect the dots.
I'm just confused because, you said not all lines are straight, so I'm trying to figure out when it wouldn't be straight and what it would look like.
Okay, good. Good question. For this type of graph, for change in position over interval, these mostly you would expect to be pretty straight lines. Let's talk about, and I'll change colors on this, and we'll get a different trend line color. So if we say that this is the car, so this is an object that's moving at constant velocity. What if I take some data for the marble? So in the first 1 second interval for which I measured, the marble moved this far. And in the second 1 second interval for which I measured, the marble moved this far. For the third interval in which I measured, the marble moves, or I measure it to move this far. And then for the fourth, I measure it moving this far. Thinking about that marble, thinking about what's happening to it, what do we know about its velocity? It's increasing. So what do we know about the distance that it is traveling in each interval? It should increase. It should move a little bit further each time because its rate of travel is increasing. Now, I see two potential trend lines here. Sorry, my big fat head's in the way. Well, actually, no, I don't. I only see one potential trend line. What trend line do you see? Up. I see something like that. And I meant to I meant to use a real line. Now, does that connect the dots? No. But for this, actually, my data is pretty good. My data comes pretty close. The amount of aberration there is pretty remarkable if I'm using fairly primitive tools. I know, when I think about it, that line should be straight and that line should be a positive slope. Because if I think through what that line is showing me, it's showing me how far it moves in each time chunk, and I know that should be increasing. Would there be any circumstances under which that line can be curved? boy, in my adult little brain, I cannot think of one right now. Not for this type of graph. Now let's talk real quickly about this one last idea, which is what you, and this leads to a great conversation on your conclusions in labs. So what you know, what you actually see in your data, and the meeting thereof. So I guess this is bias. This is the bias talk. At some point, you always have to have the bias talk. You come in, okay, that's kind of a joke. It wasn't all that funny. It was probably the delivery. You come into everything with a preconceived notion. Every interaction with another human being, every approach to any data that you examine. Once you leave the realm of pure numbers, you are imposing what you think about that data on the data. You cannot escape that. You always have to be aware of it, but you can't escape it. So, if I have the marble, and we're now just looking at a position time graph. Pardon all spelling and messiness. Okay, so we're looking at a position time graph. Where is the marble at each point in time? So this is no longer the how far did it travel in each segment. And we know, let's look at the car. We know that the car, let's say my data was something like that. And I can make a pretty reasonable best fit line pretty much straight through that data. I know. And that pretty well illustrates the trend. That's not bad. Let me make this into it. Oh, no, I don't want to do that, actually. So now for the marble, let's say I get something like that. And you probably don't even have that many data points. Okay. What do I know about the motion of that marble? What do I know about its velocity? Is it constant or changing? Changing. So I know right off the bat that this trend line, this best fit line, is not going to be straight. I know that. No, you might not have known that going into the lab. But you know it now, having had this discussion. What would we expect that line to look like now that we've had this conversation? Well, curved, there are lots of ways to be curved. You can be curved like this, you can be curved like this. So the trend line here, if we made a curved line that more or less fit this data, well, you know, I'm starting somewhere here, I'm ending somewhere here. If I sort of shoot the middle, that's not terrible. Actually, that's not, okay, that's actually pretty good. Okay, so that's, I was trying to actually make it worse. That's actually pretty good data. It didn't work out. And that fits. So here's where that fits. This shows something that is starting off slow and its rate of speed continues to increase until I stop measuring. And that's exactly what we know happened with the marble. Okay, so my expectation is that I'm going to have a line that looks like that. And hey, my data reflects that. Good. Now, what if I have data that looks a little bit more? Let me get rid of my red data points, or let me at least throw out a few of them here. Get some really screwy data points. Let's make this terrible. Okay, there. That's pretty bad. Let's get rid of the blue, maybe. And that's a little bit less confusing without the blue. Okay, so I've got this whack job for my marble. Where's my best fit line? Oy vey. Now, looking at this, you could say, oh, well, this is a straight best fit line, and that's not actually a bad trend line for the data that you have. There's a problem though. You know that this should not be a straight best fit line. So where is the intersection of knowing in general what your trend line should have looked like, looking at what your data honestly tells you, and not too badly superimposing your own bias on the data? Well, if I really, in my heart of hearts, I'm honest with myself, what does the trend line look like for this? Maybe? Probably. Now, is that what I think the trend line should look like? Heck no. So then my job in reflecting on this is to say, I'm aware that the data should show X. However, my data clearly doesn't. And when I make a line of best fit through the data that we did collect, I get a result that would show the object doing blah, 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 blah. That's not what the object did. I suspect that issues arose with hand-eye coordination, with hitting the stop on the timer fast enough, or my group mate kicked the marble track while the marble was going, or we lost, I don't know, a tribble ran through. I don't know what happened, but this and this and this all happened. Yeah, we had an earthquake in Ohio, 4.2 magnitude. It was crazy. The marble went backwards. Okay. Your job is to reconcile what the data should look like, what actually happened, and what the data should tell you, what the data is actually telling you, where those things don't overlap, and why. Make sense? Okay. So, with that, let's talk about one more thing. When it's not moving at constant velocity, when it's changing its velocity, it's accelerating. And you already know that as a vocabulary word. So it's the change in velocity over a time interval. We typically at this point are still talking about average velocity, change in velocity over change in time. And that's the same as your final velocity and your initial velocity divided by how long it took you to get there. 0 to 60 in 3,600 seconds. I had a rabbit. It was my first car. That was about her rate of acceleration. Acceleration. So we said motion can be positive or negative, and that's all about whether you're moving towards your arbitrary zero or away from it. Think about that number line. Acceleration can be negative or positive, and that's where we want to be careful. Oh, so careful. So this actually oversimplifies it, so let's talk about acceleration. If I give you a graph like this, and I tell you that this is the velocity, and this is the time. So we're now graphing velocity time. 0 meters per second, 10, 20. This is the worst graph you'll ever see. I don't graph on Doceri either. 30 meters per second. And 30 meters per second is a good highway speed, by the way. That's something like 59 kilometers per hour. No, more than that. Anyway, 30 is a good highway speed. So if from time 0 at 0 meters per second, you accelerate to, well, hold on. You accelerate like this. So here you're going 0, here you're magically going 30 meters per second. What does the slope of this line give you?
Acceleration.
Bingo. Because the slope of this line is now your change in velocity over your change in time, which is by definition acceleration. So it's the handy little trick where when you have a position time graph, slope gives you velocity. When you have a velocity time graph, slope gives you acceleration. Is this object accelerating at a constant rate or at a changing rate?
Constant.
I hear both. Who has the confidence of their convictions? The line is supposed to be straight, if that helps. Constant. Okay, so because the slope doesn't change. If the slope doesn't change, then the acceleration is not changing. And that, I think, is really helpful because then you can look at the slope and go, okay, well, is the slope a large number or a small number? Okay, if the slope is a large number, the acceleration is heavy. So here is, here is somebody who is very fuel conscious accelerating. Here is somebody who grew up driving in heavy city traffic and merging on Pittsburgh Parkway is accelerating. Whoops. Okay. This is a lead foot. That is stomping on the gas pedal. Bucket of water, bucket of water.
How we do graph?
Oops. This is what we just talked about. When you are graphing velocity against time, you show acceleration. And this is, the tremendous secret. I think it was on your SLO test, too. This is a line. This is a velocity time graph. Okay, great. Let's look at point A to point B. Acceleration positive or negative? Positive. Slope of the line is positive. Good. And on this y-axis, this is 0 velocity. This could be anything. This could be a gazillion meters per second. I'll say it's 100. That's crazy. Okay, from B to C. Acceleration? Wait, what?
It's like positive from the one end.
Yeah, it kind of is positive and then it levels off. Overall, the acceleration in that segment, if I do that, is the accelerate. Okay. Let me see how. Ha, I heard it. 0. Slope is 0. Is that object still moving? Yeah. Yeah, it has a non-zero velocity. Okay. Well, I guess we'll wrap this up tomorrow and then do algebra like crazy. Hey, folks, have a good day.